I will be explaining in some detail the overall architecture of the Kirby rover, which we use for the ERC 2023. And I will be explaining the electrical schematics, like the electrical overview of the rover and how everything is connected together. So here you can see what is called the mega chart, which contains every connection in the rover, or most of the connections. So first let's get in the middle of it. So the rover runs on a Jetson, which is the Jetson Xavier AGX. I could even write it, Jetson Xavier AGX. And it is then connected to multiple peripherals. So let's get into the vision first. So for the vision, it is connected through a custom Ceredes CSI interface board. So this board here can communicate with a certain number of cameras. So I can give you some idea of how it looks like. It's something like this, and it can interface with a multiple number of cameras. So I would, for next year, I would change this board because it's not very good and it's quite hard to configure. So it would be a better idea to try and see how to use cameras that does not use this interface, because there were many issues with disconnections of the cameras or cameras crashing after a while. So please, I would really change this interface for next year. And then we have also two depth cameras. So the first one is an OAK-D stereo depth camera, which is used in front of the rover. And we have a Reelson stereo camera HD Intel D405. So this one is used on the end effector on the arm. Okay. So yeah, actually there's a wrong connection here. This one is connected also through the USB hub. Okay. Oops. So yeah, it's not very good looking right now, but yeah. So let's just put it like this. So this is also connected to the USB hub, and the USB hub is directly connected to the Jetson, and this is a powered USB hub. So this means that it can give quite a bit of power, and it's powered by the power supply here, which is 12 volts. The Jetson itself is powered through the 15 volts regulated supply of the power supply. So afterwards, let's go into the Ethernet side. So this year we don't use an Ethernet hub, but we use directly the Ethernet hub that is connected on the antenna. So we have here an antenna which has also an integrated Ethernet hub, and everything is connected on that antenna. So we have an Ethernet port that goes to that antenna, and the antenna itself is powered through 24 volts from the power supply. So it's 24 volts regulated, of course. And then the antenna is connected to the science part, so to the drill. It's connected to the LiDAR, and it's also connected to the Ethernet of the arm. So for the handling device here through the Ethernet. So we really use this as a USB hub this year. So let's look first at the LiDAR. So the LiDAR is also powered by 24 volts, and it's communicating through the Ethernet interface through the antenna. For the science part, we have a drill, and so I will just talk about the motor side for now. So for the science part, we have a drill. It's connected through EtherCAT, so also through the Ethernet hub of the antenna. We have multiple motors. So the first one is the most. Here we have one single board which contains two Maxon controllers. So it contains a Maxon controller for the drill rotation and also for the descent of the drill. And the second controller contains the static tube plus science module descent. So this is because the science part of the rover has a two-stage descent. So the first stage will put the drill near the ground, and the second stage will have the drill go into the ground while it is rotating. So we decouple the movement of the drill so that we can go up. We can really get the dirt up into the drill without having to turn the other way and so on. So we can decouple the movement. So this year I think for ERC 2024, the drill will probably be redesigned. So this might not be relevant anymore, but I am just documenting this just in case someone wants to reuse the drill for next year. Okay, so now let's move on to the robot arm. So the robotic arm is comprised of multiple controllers. So we have Maxon controllers, dedicated Maxon controllers for the joint 1 and joint 2, so G1 and G2. They all have Axim2 absolute encoders for having the absolute orientation. And then we have one board which contains 3 Maxon controllers. So these are for G3, 4, and 5. They also have their own encoders. Of course, they all communicate through the EtherCAT bus. And finally, for G6, gripper, and servo, we use another board which has 3 Maxon controllers. So that's for the structure of the arm. It is powered through the with the motor. So it's this here, which is 24 volts unregulated. So this might be a bit unclear, but this is from the battery, directly from the battery. So it's not 24 volts actually. It can vary from 21 to 29 volts because these are LiPo batteries. Not LiPo, but I don't remember what chemistry it is, but yeah, these are batteries, so it's not regulated and can vary. The voltage can vary a lot depending on the state of charge of the battery. Okay, so that's for these motors. And then for the navigation, we use the CAN bus this time. So it is connected to the USB hub of the Jetson here. And this is a USB to CAN. Like it's just a standard USB cable, but the controller itself has a USB to CAN module. So for this, we've designed our custom PCBs here, which can contain 2 Maxon controllers. So let me just open this PCB so I can show you. So these are the nav controller interface, and you can look at this PCB here. So this is the PCB that will be interfaced with 2 Maxon controllers. So there's one here for the steering and here for the driving. And so here you can see. And the steering has an absolute encoder, so you can know the orientation of the wheel very precisely. They all communicate through the CAN bus and are powered also by the 24 volts unregulated from the battery. Okay, so for the connections of these motors here, for the steering module, we used a lot of connections. So they are the encoder, incremental encoder, which is internal to the motor. We used the Hall sensor inside of the motor, as well as the absolute encoder and the motor connections itself. The driving only has Hall sensors and the power connector. So you can have a look at this PCB, which is in the rover, if you want to have more details. So I've also added some text here for which is what. So in the case of the steering, we need to connect everything. So the actual power for the motor, you have the SSI, which is for the absolute encoder, so the Axim2 absolute encoder. Then we have the Hall sensors and the incremental encoder, which is inside of the motor. So this is for the steering, and for the driving motors, we will have only the power here and the Hall sensors. Right, so this is for the navigation. Now let's move on to the avionics side of this project. So the avionics is comprised of multiple nodes here. So all of these nodes are can be described by this single PCB and also another PCB which comes on top, or multiple PCBs that come on top. So these PCBs here are these nodes here. I've also written their IDs because they are also configured in a CAN bus, and each node would have its own CAN ID. So they are connected to the Jetson through the 40-pin header. So the Jetson AGX, so if I type Jetson Xavier AGX, you can have a look at how it looks like. So we use the development kit, which is this one. and it has a 40-pin header here. And we've designed a custom PCB which is attached on this 40-pin header and exposes two CAN interfaces, right? So we can then communicate through the CAN bus with the Jetson through this custom PCB. So the Jetson has an ID of 0, which is what we've decided on. It is then connected first to the node for the handling device, then to the navigation node, afterwards to the two science nodes. So we've decided to divide it in this part because the science nodes had to be removed from the rover for different tasks. So for example, for the navigation task, we don't want to have the drill and we don't want to have the container on top. So we remove all of the science parts, which means that we only need to sever this connection. For next year, I would strongly suggest localizing every node at the same location if possible, so that we can simplify the design, if possible, of course. So it will really depend on the design. So then these PCBs here are connected to other PCBs, which you can see in green. And these are hats or sub PCBs that will come on top of the main PCB and will be connected here on these spots. So for example, the handling device node has a voltmeter at the end effector at the end of the arm. And then this voltmeter will communicate through the CAN bus and will communicate through a receiver, which is connected to the PCB here, the main PCB. It is also connected to a level shifter, which can be used to control a servo at the end effector. Navigation node has an AMU. So this is for estimating the heading of the rover. So this is an inertial measurement unit. In our case, it's a 9-axis AMU. It is also connected to the RP2040 hat. So this is a microcontroller, another microcontroller which communicates through I2C with our sensor, with our board. And this allows us to control a set of addressable LED strips. We also have a potentiometer here, which is used to measure the angle of the differential bar of the pivot of the differential bar of the rover. Then here have the science container. So the science container PCB, it's still this one. And this one communicates with a mass sensor for measuring the mass on top of the container. And it is also connected to another science node, which is then connected to multiple sensors. So it's connected to a spectrophotometer, and it's also connected to a mass sensor similar to this one, as well as two other sensors which communicate through the Modbus protocol. So these two sensors are connected to an RS485 interface, which itself is connected to this node. So I forgot to put it here on this schematic. All right, so that's it for the main logical part of the circuit. Now we also have the power part. So we have designed a custom power supply, which generates these 4 voltages. And this power supply is also connected to the safety system. Okay, so now I'll just have quick words about the safety system. So this is the safety system that we've used for Kirby. It's not perfect and there were some issues, so I will discuss some of the issues that we've encountered. So it's a very, very simple safety system. We have the battery here, which goes inside of a circuit breaker. So we used, I think, a 50 amps circuit breaker in our case, 50 or 40 amps, I don't remember. And so this circuit breaker just acts as a way to limit the current. So if you don't know what it is, you can just type circuit breaker, and these are just like fuses that can be reset with your finger once and are triggered by an excessive amount of current. It then goes through an automotive relay. So this is your standard, very cheap automotive relay. I think we used a one that was rated for 70 amps, which is more than enough. So these relays are basically switches that can be activated by a certain amount of current. So here the terminals 30 and 87 will conduct only if the emergency button here has only if there is current that can like power an electromagnet, an electric coil inside, which closes the circuit. So the emergency button here, if we press it, it will cut the current to that electric coil, and it will close. It will open the circuit, which is what we want. So there is one relay here before the power supply, and there is another one after the power supply. So why do we do that? This is because we want one that can shut down the whole system, while the other one here is used only for shutting down the motors, but not for shutting down like the Jetson, which is powered by the 15 volts, or the LiDAR, which is powered by 24 volts. So we want a button that only shuts down the motors. So this is what we did last year, but there were some issues that I will explain now. So first, in terms of safety, we had some issues with the circuit breaker where it was not triggering even if we accidentally reverted the input here or the output here. So I don't know where the issue is. I have some ideas, but we had some issues where the polarity here was not correct. And in this case, it actually blew the fuses and the diodes instead of triggering the circuit breaker. So this is something to investigate. I'm not sure where the issue lies, and maybe it's not the safety system, but more on the safety part of this circuit, which should be changed. So another issue that we had was that the motor shutdown button was not like shutting down only the motors, but also shut down the Jetson. So my hypothesis is that when we shut down the motor, there is some kind of spike because of the inductance of the electric coil of that relay here. Might be some spike which trigger the safety system of the power supply, because we have then a spike at the output which is greater than the input, and this shuts down the channels, or those are very small, like a small inverted spike. It cuts the current through the Jetson, which turns off the Jetson for a very short amount of time. So this is also something to investigate for next year. I'm not sure what the issue is, but it might be possible to just solve it by adding a large capacitor at the input connector of the Jetson, like 1000 microfarad or so. So yeah, so this is basically what was done last year for the safety system. And yeah, also for the gauge, like the wire gauge for the cables, like how wide the cables are, what we used was AWG12, if I remember correctly. So they are fairly large wires, so 4 millimeters square, and this is what we used for transferring the power from the battery to the power supply and so on. So please use fairly large wires so don't have any issues with wires burning or with a large drop in voltage and so on. Okay, so there isn't much else to say here. And these tabs are not really useful because I've already explained them in the mega chart. So yeah, so if you have any questions, please tell me, and I will give you more details. I know that this is quite abstract because these are only schematics, but once you get your hands on the rover itself, you will start to understand where each connection is and what is what. So see you in another video, and I hope you've had a better grasp on the electrical structure of Kirby.